Thank you very much. Welcome everyone to our talk about exploit generation and JavaScript analysis automation with WinDBG. We really tried to come up with a longer name, but we couldn't. So, a few notes about myself. I have way too much public information about myself on Google, so just search my name and you will know everything about me. But I have a wife, a 3-year-old son. My number one hobby is hiking, usually, so I try now to sit every time next to the computer. And I have plenty of unimportant certification and some more useful ones, like the ones from offensive security. And Miklos?
Hey, so good morning. I'm mostly off the grid, so I'm a kind of paranoid person, so you will not find me too much on me on Google, I can promise. Just a little bit of information about myself. Yeah, I'm married, I have 2 kids. And myself, I'm not so much of a cert collector, although I'm interested in a lot of trainings and I typically do attend them, but the one that potentially is relevant for this presentation is JAX, reverse engineering malware. So as for hobbies, I'm also kind of the hiker, and I typically try a new sport every year. Back to Csaba.
Thank you. So our first part of the talk is the automated exploit generation with WinDBG. So we all know, at least people who anytime wrote or tried to write an exploit or develop an exploit, how annoying it can be sometimes. So it's a heavily manual intensive process to dig inside the debugger. And we all know the challenges when you start a debugger, you start the process, and you realize that, oh, I forgot to put in the breakpoint. And then you start over, and then you realize, oh, I did a typo in my exploit. Okay, let's start over. Stop the debugger, start the process, attach the process to the debugger, continue, crash it, and so on. It can be really time-consuming many times and also frustrating in some cases, especially when you are progressing towards the end and you tend to rush. We tend to make more and more mistakes in our little exploit code. On the other hand, talking about classic buffer overflows, so not talking about kernel exploits or difficult heap exploits on browsers and heap string and all these fancy stuff, but if you look on classic buffer overflow exploits, it's quite standard process how you really develop an exploit. So you usually start with finding the EIP or finding out that you can control EIP. What is the offset on your buffer to overwrite EIP? Then you will start to examine the memory layout, how much space you have in various places, which registers point to your buffer. Then you will try to somehow jump to your shellcode with using one of the registers. Then you will generate the shellcode, usually probably with Metasploit, and at the end put it all together and you will get a working exploit. But this is usually, there are some corner cases when you need to come up with some really creative ideas, but if you look the majority of classic buffer overflows, I think this methodology covers most of it. So I was thinking why we cannot automate this entire process. There are tools that are already doing some part of it, like trying to help you to develop exploits, but none of them automating the entire flow. So my goal was to create a tool which can do the entire exploit development for you from a crash till a working exploit, and if possible with 0 manual interaction. So I wrote a tool in Python which uses the PYKD library. And maybe a few words about this one. This library is developed, I believe, by a Russian team. And basically, it allows you to interact with WinDBG directly from Python. There are two ways to it. You can either run Python scripts with this library inside WinDBG, or it allows you to actually invoke WinDBG, start the process in WinDBG directly from Python. So you don't even need to open WinDBG for anything. And it's really helpful. It has a very good and rich API. You can query the values in the registers, search the memory, do a whole lot of stuff which can help you to explore the environment. And I already released the tool, but we will share the link after the talk. So what the tool can do as of right now, again, this works for classic buffer overflow, so nothing more. It can also bypass ASLR with the method of, it will try to look for DLLs which doesn't have the ASLR flag. So we'll look for modules where the memory is not randomized upon load. And if you want, it can try to search only those ones for assembly code. It works for file and network-based exploits. It's important because when you automate it for network-based exploits, you have to start the process, wait a little bit, and then send your exploit. On the other hand, on a file-based exploits, for example, when opening, let's say, a MP3 list file, you need to generate the file and then open the process and load that file to the process. So the workflow is a little bit different. And it can basically develop a working exploit from a simple crash. And again, it can automate anything, and you don't have to start WinDBG. You can just run this script, and it will do everything for you. So how does it work? It will start the process in WinDBG from Python. It will send in the crash, and I will talk about later on how you give the input to it, how you actually write the exploit so it can work with the tool. It will find the EIP offset. It will analyze the memory. It will find registers pointing to your buffer. It will find all the bad characters, which is not supported by the application, or which can make your exploit not work. It will find ways to jump to your shellcode. It will try various methods like jumping to a register, calling the register, or pushing the register value and returning to it. It will generate the shellcode. Now, this part is where it uses Metasploit to generate the shellcode. At this point, it's hard-coded to calc.exe as a shellcode, but you can essentially replace that line with anything. But you need Metasploit to generate the shellcode. And it will generate the shellcode with knowing all the bad characters. And at the end, it will put everything together, and it will successfully run the exploit, and it will also save the exploit for you. So if it's a file-based, it will be already saved because the file is already there. But if it's like a network-based exploit, it can save it for you, so you can use the exploit later on. I have a demo. We didn't sacrifice any animals for the demo guts, so we decided to go with videos and not with live stuff. So this is where the application starts. Let me zoom into. So it will start with sending in a pattern. You're probably familiar with this from Metasploit. It uses its own pattern generator, and it will identify the offset for the EIP overwrite. So let's continue. You can see that it's restarting the application in the background. For the demo, I'm using Minishare. It's a very old application exploit, but it's very good for demonstration. And then it will start to find bad characters. And it will also log you a bunch of other outputs to the screen, so you will have a very rich logged information for later use in case you need. So now it will try to find all the bad characters. It takes a few seconds. It's still much, much faster than doing this by hand. So if we zoom into it, so we can see that it found all the bad characters. It saved it for later use. And basically, at that point, it already knows which registers point to your buffer, and it will start to search all of the modules, all of the loaded modules for usable assembly instruction, how to jump to your shell code. And by default, it will try to find jump ESP in this case, or jump to the specific register. So let's continue. So let me zoom in one more time. So it searched through all the DLLs, and it recorded all the memory location where it found usable instructions. And then it will generate the shellcode with the use of Metasploit. And basically, at the end, it successfully crashed the application and can launch Calc. And the only thing I gave to the application initially, it was the crash information. So how do we use this? So there is some pre-work that has to happen. You cannot just take any POC code that will crash the application and give it to the tool, because it cannot interact with it. I came up with an exploit class, and there are some functions inside to it, which has to be populated, mainly the exploit function, which basically defines how you crash the application. Again, this is written in Python. So basically, you have to populate this function in order to work. And the other thing you have to do is you have this self.buffer. The buffer is an internal variable to the class, and that basically, it's a list of strings which are the building blocks of your buffer. So it's mainly split to 3 places: before EIP override, the EIP override, and after the EIP override part. And the reason I have to have this class is because I have to modify the buffer on the fly based on the information I gathered during the analysis. So that buffer is constantly evolving, either with the patterns or with the bad characters triage and so on. And there is another function which have to be populated in case of network-based exploits. That's the save function, in case you want to save your exploit for future, and why you wouldn't want to do that. And it would be basically the very same function than this exploit. It would be just writing out everything you put here. You write it out to a file, and you write out also the buffer to a file, and that's it. And in case of buffer file-based exploits, you already have the file on the disk, so you don't need to save it additionally. I tested it with bunch of applications. I have other videos as well, and I will post them later on, probably in YouTube if anyone is interested. It works pretty well, reliably. Probably a big challenge is if you need to interact with the application in order to crash it, then it can be a challenge. But generally, it works. And for the future, based on this, I plan to add the SEH based overflows, because I think those can be automated as well. Add more logic to make more tricky jumps to the shellcode, and maybe also add DEP bypass with generating rope chains to the exploit. So that was my part. Thank you.
Okay, thank you, Csaba. So, funny thing that Csaba and I both attended the same most awesome Windows exploitation training provided by Carl, and where we got our inspiration from. Yet I'm going to look at a completely reverse angle of it. So, how we could use automation for reverse engineering tasks. So, how many reverse engineers do we have in this room? Hands up. Good. I see a few hands. So, now you wouldn't want to waste your time on reversing non-malicious code, would you? So, what's the workflow? You get some sort of hint from a particular code as being malicious, either from a sandbox analysis engine, never mind whether it's free or commercial, or the level 2 team from the blue team notices bad behavior. So once the thing lands on your desk, you need to figure out how it works and what it does, whether it is already known or not. And in the case of browser exploiting malware, it comes down to figuring out the JavaScript part of it, isolating the shellcode, understanding the vulnerability, and honestly, it's quite a time-consuming process. And it is coming with a number of challenges. So one of them being is that it can be analyzed in the browser's own debugger, but then you have to spend some time figuring out the correct breakpoints you have to set up. It can be extracted from the page and you're using an external JavaScript engine to analyze the code and to patch it if needed. And last but not least, you have to sometimes deal with the problems of code containing anti-debugging or anti-reversing techniques. Thus, word of warning, so we're not going to unleash a one tool solves all problems of your reverse engineering problems, nor are we going to fully automate the whole process. I don't believe it's entirely possible either. After all, it's called reverse engineering, right? So what we're going to do is do a bit of code deobfuscation, and the methodology goes like, okay, you want to catch the function before the execute. You place some sort of breakpoint. If needed, you overload the functions. You locate the exploit code, and you understand the shellcode. So our approach to this was to put together a tool that can automate the deobfuscation. Now, JavaScript obfuscators use several techniques. Variable name mangling, character substitutes, function expressions, arrow functions, lambdas, ifs, and most often evals, so evaluates. Worthy of note that gladly, since JavaScript is not a class language, you don't have to deal with reflections. So there are a dozen or so JavaScript deobfuscators out there. But we wanted to come up with a simple yet effective solution that is solving the issue of reversing natively. So are we going to reinvent the wheel here? Well, maybe, but our wheel is going to be a bit different. So we want to make it impossible for the JavaScript code, like the malicious code, to figure it ever out that it's being debugged or it's being reversed. we want to have the malware run in its most natural environment, that is the browser itself. So it would be very nice if we could somehow get it to stop at the point where the exploit starts to run, and we want to have the minimum manual interaction. So this pretty much comes in handy when the JavaScript code is trying to run a browser exploit with a heap spray and a use after free situation, for example. So, well, breaking out of the jail, breaking out JavaScript code from its natural environment doesn't always work as good. So why not? Why don't we break into it? And the idea is to harvest the awesome powers of WinDBG and a bit of Python code that goes along with it, using the same PyKD WinDBG extension. And the code is hosted at GitHub. We will see at the final slide. So what can it do for the moment? It works for IE11. Deobfuscates eval-based code, stops at the exploit. Each session is being logged to a new file, and most of the process is fully automated. So, since we want to break into the jail, we want to find the right function. So, word of warning: this code has to be maintained in the sense that each major version of a browser and each vendor has a very different implementation of the JavaScript engine. Obviously, very different debug symbols that go along with it. So we're going to do to try to figure out the JavaScript engine's points where actually evaluation is happening, and we're going to use dynamic arguments for that to make sure that we don't confuse the source code with the actual dynamically evaluated code. So, finding the pointer to the argument is the next thing. So you want to make sure that you're trying to, log whatever is being already evaluated, not, the string that goes, in there before the obfuscation happens. So once you figure out the argument, you need to figure out the location to it. And I'm not sure how many people are familiar with different WinDBG extensions, like Mona, for example, is one of the great tools, and it helps you a lot with finding X in memory. But as good as it is, unfortunately, I couldn't figure out for the life of me how it could give me in a most simple way to get a pointer from the current registers to a memory address. So for this reason, I created a Python helper application, this chain.py, and it works like you provide the address when you want to point to, and then the level of recursion or iterations of pointer to references, the starting register that you want to start from, and a range of words that you want to come up with. So this will help you in many cases. Most often you will use either the ESP register. Well, obviously most things are on the stack, or in certain cases the ECX register, which contains a pointer to this. So all in all, it's a longer story, but you figure out that the most obvious codes from the symbols from Internet Explorer don't point to what you're after, and you have to dig deeper. So at the end of this presentation, the code that we're releasing is not just the code, but also the methodology. So we're providing a full tutorial on how you can actually figure these things out, and later on you will be able to maintain for different browsers. So once you have the logging breakpoint, you start to automate things. I'm not sure how many of you have you tried to debug directly into the browsers. It's not the most easy thing, and attaching to debugger even is not simple. So we put together some WinDBG script files that create a unique log file for each session. Ignore the unneeded breaks. Make sure that you set up the correct levels of exception handling. So you ignore the ones you don't really care about, and you only cache those ones that you need to. WinDBG syntax is not exactly user-friendly, so I put together one short method to encompass this in a two-liner. And ultimately, you set up the breakpoint. So again, time is short, and we didn't pray long enough for the demo gods. So we have here a simple video. So what's going to be here on the screen is the WDS file. So the script, the WinDBG script, sets up the breakpoint. Now this is the simplest possible version of trying to figure out how eval works. As again, you want to have a dynamic argument to it, so you don't confuse it with source code. So as you go further on, and it seems to work, then you try to go a bit of a stress testing to see if you found the correct thing, and if it works for a number of quick succession of calls to eval. And further on, if you really want to test it, you can use an eval bomb that does a recursive evaluation until the stack overflows. Actually, it will kill the browser. Here's an example of a simple obfuscation. So all it needs to do is actually you run this ilog.ps. This is a PowerShell script that does the automation of attaching to the debugger, and you use your browser as you would normally. So you just you navigate in the browser window, and as soon as the eval starts, it is getting logged to the logger window. So this is the first stress test, making sure that it's able to catch up with what's happening, and we're not using invalid pointers. And here's the already deobfuscated code at the bottom of the screen from the next sample, and ultimately we can try to see how it handles a serious stress test. So basically, this is the recursive eval, which is, as you'll shortly see, completely crushed the browser. So it can handle even very stressful situations, and what you get is well, ultimately the browser crashes. You get a log file out of it, which we'll hopefully see in a few seconds. So you get a new log file for each session that you run this evalizer. This is what I named it. So here are all the outputs, and somewhere in there you will see the actual deobfuscated code as well. And if you ever wonder how many times the browser was able to handle the recursive evals, then you can see that it's 9,000 times before the browser decided to fully crash. So this is just the proof of concept. So now actually let's see an actual exploit. So this is going to use a heap spray with a use after free. So this is the original code that I was working on originally when we experimented with the exploit, and this is a very heavily obfuscated, multiple times obfuscated version of the same code. So I think it's obfuscated like at least 3 or 4 times with different mechanisms of obfuscation. And again, we're firing up the equalizer. And once we open up the obfuscated code, not only you get the deobfuscated string in the output, and also later on you'll see the log file, but also you're getting a breakpoint into the virtual protect call that is actually the final step in the ROP chain. So it's a bit tricky to figure out how to put together the breakpoints for the virtual protect in order to differentiate the real virtual protects from the crashes, but that's also going to be released in the code. I don't have time for that. But the point is that it's very nice because you get at the same time a output of the already deobfuscated code, and at the same time you get your hand on the point where it actually crashed, so you can immediately analyze the malware itself as it's trying to do its badness. So for future plans, we want to document some methodologies for Edge and Chrome as well. The same thing works pretty much the same. It's just different symbols. Mind you, if you want to work with Chrome, then you have to understand that the Chrome debug symbols are almost 1 gigabyte inside. So you better have a very large virtual memory machine. Okay, and here are the source codes. Both our parts are released on GitHub, so that pretty much concludes the demonstration and today's talks. So if you have any questions.
To anybody?